Everyone, in today's video we will be solving a problem based on bending stress. So here this is the question. So here it says that a circular beam of 120 mm diameter is simply supported over a span of 10 meter and carries a UDL of 1000 Newton per meter. Find the maximum bending moment produced. So here a circular beam is given, so the cross sectional area of this beam will be like this, and here the diameter is 120 mm and is simply supported over a span of, okay, so it's a simply supported beam over a span of 10 meter. It's given in the question, okay, and it carries a UDL of 1000 Newton per meter. So here the UDL acting over this beam is 1000 Newton per meter. So what we need to do is we need to find the bending stress. First I'll write the given data. So here D is nothing but the diameter of the beam is 120 mm and length is given, that is nothing but 10 meter, and here what we need to find is bending stress, that is denoted by the term sigma B is equal to this one. Now we know the formula for the bending stress, that is, so the bending equation is equal to M by I is equal to sigma B by Y is equal to E by R. So this formula is known to us. So now here M is nothing but the moment, I is the moment of inertia, sigma B is the bending stress, and Y is the distance of the neutral axis to the upper layer of the beam. So here see, in this equation this term is not given. This is nothing but the modulus of elasticity and this is the radius of gyration. So we'll be taking this equation. So M by I is equal to sigma B by Y. So we'll be using this equation for finding the bending stress. Now M moment can be found because see, in the question it's given that it's a simply supported beam and it carries a UDL. So the formula for finding the moment is WL square by 8. So here W is already given in the question, that is nothing but 1000. So here 1000 into the length of the beam is 10 meter, 10 the whole square upon 8. So we'll be getting a value around 12.5 into 10 to the power 3 Newton meter. Now we have to convert it in Newton mm. So here 12.5 into 10 to the power 6 Newton mm. So now here, since now next what we need to find is, okay, this one we already got. Now next is to find the I value. I is nothing but the moment of inertia. So moment of inertia is equal to, for a circular section, see it's a circular section, so for a circular section moment of inertia the formula will be pi by 64 into d to the power 4. So everything is known to us here. Pi by 64 into d is nothing but the diameter of the cross sectional area is 120 mm, is 120 to the power 4. So we'll be getting around value is 10.18 into 10 to the power 6 millimeter 4. The unit of the, always remember this part, okay, the moment of inertia unit is mm to the power 4, or it can be meter to the power 4. Now next what we need to find is, we need to find the value for sigma B. So now our next is to find the Y value. So here y is equal to d by 2. See, it's given in the question the cross sectional area, and the cross sectional area is 120 mm. So here we know that this is the neutral axis, and D is nothing but the distance from the neutral axis to the upper layer of the beam. So here if D is equal to 120, then this half will be D by 2. So D by 2 will be 120 by 2 is equal to 60 mm. So now we have all the values with us, just we need to put the values in this equation, that is m by I is equal to sigma b by y. So what we have to do is we have to shift this y this side, then the equation will be is equal to m by I into y. So just we need to put all the values here. The value of m is nothing but, what was that, is this one, 12.5 into 10 to the power 6. So 12.5 into 10 to the power 6 divided by the moment of inertia value is what was that, this one, 10.18. So 10.18 into 10 to the power 6 into the value of y is 60. Now what we have to do, this one and this one will get cancelled, and we'll get the value around 73.68 Newton per mm square. Okay. So in the question what it says that we need to find for the bending stress produced. So here we got the value for the bending stress produced in the circular beam. So this is our answer. Thank you.